Hello, and welcome to Module 4.2a, Rate of Change and Slope. Our objective for today is that I can calculate and interpret the rate of change. What is rate of change? It is how a quantity is changing with respect to a change in another quantity. If x is the independent variable and y is the dependent variable, then the rate of change is the change in y over the change in x. Now, when we look at a data table, we're going to see them laid out in one of two ways. Either you have two columns side by side like this. In this case, your left side is your x value and your right side is your y value. Now, if I'm trying to find the rate of change and I have a table like this, I'm going to use these little chevrons, these little triangles, and I'm going to find out what is my change from one row to the next on both my x values and my y values. So on the x side, from 10 to 20, we're adding 10. From 20 to 30, we're adding 10. And from 30 to 40, we're adding 10. On the right side, we're going from 2 to 4, so we're adding 2. We're going from 4 to 6, adding 2. And from 6 to 8, we're adding 2. So if I were to calculate this rate of change, it's the change in y, 2, over the change in x, 10. And when I simplify that, I get 1 over 5. Now, the next question says, if we use non-consecutive rows, will we get the same rate of change? So if I go, let's say, for example, from 2 to 6, my rate of change is going to be plus 4. And on this side, if I go from 10 to 30, my rate of my change is plus 20. And if I do that, 4 over 20, I reduce to the same 1 over 5 value. And if I were to go all the way top to bottom, and we do 4, so we're doing plus 30, and on our y side, we're doing plus 6, 6 over 30 still reduces to 1 over 5. So yes, we will get the same rate of change no matter what pairs of rows that we use. So now, letter C, we have the table showing the elevation of a hang glider over time. Is the rate of change with respect to the elevation constant? With the rate of change in elevation with respect to time, is that constant? And what does that represent given this scenario? So if we look here, we are going from 360 to 325. That's minus 35 feet. And then we're going to do minus 35 feet again to go from 325 to 290, and we subtract 35 again when we're going from 290 to 255. My x values, we are increasing by 1. So our rate of change is negative 35 over 1. And what does that represent? Well, it's feet per minute. So meaning we decrease 35 feet every minute. All right, now this is what's called the glide ratio. Um, any aircraft is going to have a glide ratio, and it tells you just without any power, how far are you going to be able to travel if you have no engines. And so this is actually a calculation that's made with even the largest jumbo jets, a Boeing 777 or the Dreamliner, the A380, any of these big, 747. All aircraft have a glide ratio, and it's a way for them to determine how close they need to be to an airport in order to make some sort of recovery or emergency landing from a problem. Now, letter D, we have the number of lawns being mowed, and we have the dollars being earned by an individual. So when we're looking at our lawns being mowed, 3 to 5 is plus 2, 5 to 7 is plus 2, and 7 to 9 is plus 2. And on the right side, we have 4250 minus 2550, and you get 17. And then from 4250 to 5950, that's another 17 that we're adding. And from 59.50 to 76.50, that's another 17. So when I do the math on this, we have 17 over 2, and we're going to go ahead and do that division, and we are going to get that is going to be equal to $8.50 per lawn. All right. Now, from the time that I wrote this problem in, somewhere around 2014, 2015 to now, inflation has happened, and $8.50 a lawn is certainly not an amount I would work. I would work for to work on cutting lawns. Back in the day, that was the minimum wage in the state of Illinois, and today, not so much. All right. So now let's take a look at letter A. This is a you-try problem, so you do it on your own, and then come and check your work against mine. So we have our x value, we have our y value, and we're going to look at what are we changing by. So from 1 to 2, that's plus 1. 2 to 4, plus 2. 4 to 5, plus 1. Our x values, we are adding 2, we are adding 4, and we are adding 2. So if I find my rate of change, it's going to be 1 over 2. You have $1 per 2 tickets. Well, you might say, hey, Mr. Boland, you've got 2 different rates there, right? You go up by 1 on one side and up by 2 for the next line. Well, let's take a look at that. Going up by 2 over 4 is still going to reduce to the same 1/2 fraction. So essentially, we just skipped the step going from 4 to 6 raffle tickets, and that would be from $2 to $3, and we went straight to 8 to 4. So this is why we need to actually do the math on this to make sure that we actually have a linear relationship and that we have a constant relationship. All right, letter B, we're going to look at, we've got gasoline being purchased, and we are figuring out what is the rate of change of this gasoline being purchased. So first thing we need to do is find what the rate of change is between these. So from 1577 to 1992, that's 415, and it's going to be the same on all 3 of these, 415 and 4.15. All right, so now to go from 4.75 to 6, that's a 1.25 increase. To go from 6 to 7.25 is a 1.25 increase. And again, to go from 7.25 to 8.5 is a 1.25 increase. And when you do that division of 4.15 over 1.25, you're going to get $3.32 per gallon. So not all that far off from what we are currently seeing in terms of gas prices around the world today. All right. So we are going to take a look at comparing some different rates of change and figuring out what it is given the context. So Jackson High School Student Council budget is going to vary based on the fundraising from the previous year. So in 2000, we have $13.50, and in 2005, we have $16.75. So that's a difference of $325 over the 5-year span. And so 325 divided by 5 is going to give us 65, and that is going to be dollars per year, and that's increase. So from that time period, your average is $65 per year. It's going to go up in that time period. Now, when we look at 2010 through 2015, we see a different kind of a change. We see a decrease. We're going from 1550 to 1325, and that's going to be a difference of, we're decreasing $225 in a same 5-year period. And so when we divide that out by 5, we're going to get a $45 per year decrease. And why could we be seeing a decrease in this time period? Well, we've talked about it before. 2008 was the start of the Great Recession, the financial crisis, so people may be less likely to spend money at a student council, fundraising events than they did prior. Now, in class, a really good question was asked, and it related to this piece of the graph right here. What does this little squiggle mean on the graph? And what that's telling us is there is a break in the graph. We are not showing any data from 0 to the year 2000. Anytime prior to 2000, there is no data being represented. And that's what that little break is showing. It's showing that, we could have had this graph where it goes way, way, way over here, even, much, much, much further than that, going back to year 0. But realistically, is there any reason for us to have a graph that shows years in which this school likely didn't exist? If we're going back to year 0, we're going back to biblical days, we're going back to days before other modern religions are even created. Any of the three, or two of the three modern religions were created, going through the Renaissance, going through the Middle Ages, even going back to World War I, World War II in the early 1900s. Do we need that data on this graph? Well, no, because this high school didn't exist back then. So when we see a symbol like that, it means that graph is being cut and we are only being shown a portion of the data that's available. Now, I would caution you against using this too often. If there is data available for a time period, you do not want to do this because it makes it look like you're trying to hide something in the data. And that would be a way to manipulate the data that's shown. So oftentimes, when you are looking at data on a controversial topic, such as climate change, you may see graphs representing data from one side or another in which they are using either graph breaks or misleading scales in order to try to accentuate their points, either minimizing the damages or the concerns about global warming, or maximizing the potential scare factor of, oh my God, this is the worst catastrophe ever. And so when you have these kind of graphs, that's a way that you manipulate the data in the way it's presented to alter how people may perceive it. So when it comes time to you creating your own graph, if you have data in a time period, you should not be using that little skip there. All right, now let's take a look at the next one where we have the average price of tickets for the Miami Dolphins. And we are going to find out, it's asking us, find the rate of change in the ticket price from 2009 to 2010. So in 2009, our ticket price was 66.74. And in 2010, our ticket price was 70.54. And so what we're going to do, we find that difference, and that's going to be $3.8 in the course of 1 year. So we're going to see an increase of $3.80 per year. So from that time period, that's our increase. Now, we want to know, when do ticket prices have the greatest rate of change? And as I look at this, from 2008 to 2009, we see that our increase is 63 cents only. And then when we go from 2010 to 2011, ticket prices actually dipped by 22 cents. 2011 to 2012, they are going up a little bit, so that's about 80 cents. It's less than $1 there. We are steady in this next year, and then we see another big dip in our prices. And so we have 71.14 going down to 65.16, 65.16. And what is that going to get us? That's going to get us a 5.98 decrease. So ticket prices are going to have the greatest difference. So that's 5.98, and this was 3.8. So this is a much larger difference. So when do ticket prices have the greatest rate of change? It's going to be from 2013 to 2014. This time period represents the greatest rate of change in the ticket prices for the Miami Dolphins. Now, This is an important distinction to make. It is the greatest in terms of its magnitude. The change was the biggest compared with a previous value. Not that it's increased the most amount, it's just it had the greatest change value. It has the steepest slope. And as you look at this, we have a little more gentle slope, but that's a much steeper downward slide there. Now, we also want to know between what years was the rate of change negative? Well, this is my first one, so that's from 2010 to 2011. And our other big one is going to be from 2013 through 2014. All right. So now we're going to go on to examples 3 and 4, and we need to determine whether the function is linear, and if it is, we want to state what the rate of change would be. So letter A, we have a change value. So we're going to see what are we changing by. So -5 to -3. So we're adding 2, we're adding 2, we're adding 2, and we're adding 2. On the left side, we are subtracting 3, subtracting 3, subtracting 3, and subtracting 3. So our value is 2 over 3, and we just put the negative sign out front. All right, so we have a -2/3. That is linear. It is the same rate of change for each of the steps that we're taking. Letter B, we're going from -4 to -3, so that's adding 3. -1 to 1, that's adding 2. 1 to 4, that's adding 3. 4 to 6, we're adding 2. Well, okay, this is a red flag. We do have different increases, different values of our y. Let's see if it's actually going to be a constant rate of change. So when we look at our x, we're adding 7, adding 7, adding 7, and adding 7. So our x values have the same rate of increase, but our y values do not. So that is going to be non-linear. All right, so now we're going to go on to letter C. And for this one, we need to figure out what is the relationship here, because I need to fill in these blanks. So I want to look at what are my values and what do I have as my difference. So my difference on my y value from 7.5 to 10.2 or 10.75, we're adding 3.25. And if I look at -2.25 to 1, we are adding 3.25. So that's a good point. So now let's kind of continue that pattern. From 1 to our mystery number, we're going to add 3.25 to it, and we get 4.25. And if I check my work and I go from 4.25 to 7.5, well, that's still adding 3.25. And then to go from 10.75, we're going to add 3.25 again. And so that's going to be 14 even. Now, what's happening on my x values? We're subtracting 0.5, subtracting 0.5, and subtracting 0.5. Well, how can I fill in the number values above if I don't have something above them to subtract from? Well, if we look at it a different way, if we're going this way, we're starting at the bottom and we're going up, what we're doing is we're adding 0.5 each time we move up. So 9.5 plus 0.5 is 10, plus 0.5 is 10.5, plus 0.5 is 11. So then if we continue that pattern going up, we're going to get 11.5, and we're going to get 12 as we move up. And so this is a linear relationship. We do have a constant rate of change. It is 3.25 divided by -0.5, and we are going to get on that a -6.5 as our rate of change. All right. Letters D, E, and F are you try problems. I would like you to try them on your own, and then we will check them against my work. So hot dogs and buns, we have an increase of 1 for each of our buns. And we have an increase of 1 for our hot dogs. So is this linear? Yes, it is linear. And my rate of change is 1 over 1, which is just 1. Because obviously, if you're eating hot dogs, you're going to eat it with a bun, unless you're some sort of monster. Letter E, we have the descent of an airplane, and we are going to look at it over time. So going from 30,000 to 29,000 is minus 1,000 feet. To go from 29,000 to 2,750 is minus 1,500 feet. And to go from 2,750 to 2,400 is minus 2,500 feet. Well, this is kind of starting off weird. We've got different values in our change in y, but let's see what happens on change in x. We're adding 2, we're adding 3, and we're adding 7. So now, if we go ahead and do the math on this, my first row is negative 1,000 over 2, which is negative 500. My second row is negative 1,500 over 3, which is still negative 500. And my third row, negative 2,500 over 7, negative 3,500, not 2,500. So we're going to make that as a correction right away. So negative 3,500. And when we do the math, negative 3,500 over 7 is going to still equal negative 500. So this is linear with negative 500 as our rate of change. We're going down 500 feet for every 1 minute of our descent. All right, now our turtle walking. We go from 1 to 2, 2 to 3, 3 to 4. We're adding 1 for each of those. Our distance, we're going from 6 to 12, that's adding 6. 12 to 15 is adding 3. 15 to 21 is adding 6. We have 2 different rates going on here, so this is non-linear. All right, and that's where we're going to stop for today. If you have any questions, make sure you bring them to class tomorrow. Otherwise, have a great evening.